Okay, so this is the second video focusing on conductors. And what we're going to do here is we're going to look at how do we calculate the potential um, inside a conductor, around a conductor, okay, in various situations. And then we're going to do an old AP Physics C practice problem, okay. For this practice problem, half the problem is going to focus around calculating or using Gauss's law to figure out the E field. But then we're going to take that information and then we're going to find the potential difference as a function of a distance x away from the center. Okay. But first, let's talk about how do we calculate potential difference. So, potential difference, okay, there's three ways to calculate potential difference. Again, potential difference is V, right? And so if it's a point charge, we talked about that in the previous video, it's just simply KQ over R, right? You may see this Q written as a capital Q, and I go back and forth between capital Q and lowercase q. Now, a potential difference when the potential energy is known. So if we know that potential energy, the potential difference is just simply subtracting, okay, or the change in potential over charge. All right. And then the potential difference between 2 points in an electric field, this is where we bring in our calculus, right? So it's negative A over B E dot dr, where r, right, will be the distance from the center. Okay, and one thing you do understand, like when you do these problems, they probably will have like a part A, calculate the electric field by using Gauss's law. Part B, what is the potential difference? Or as you can see here, we're going to have um, a sphere, an insulating sphere, which means we do have a net charge on it, surrounded by a conductor. Okay. Um, and then we're going to be asked to find various points right along the way. Okay. So the part A, B, and C of this question would have been handled when we talked about electrostatics last when we did Gauss's law. Okay. So let's just quickly, this is a great time to review Gauss's law, right? So Gauss's law says that the electric flux is equal to the surface integral of E, or sorry, not E, but yes, sorry, E dot dA, and that's going to equal the charged enclosed over epsilon naught. Okay, so one thing they like to do with these problems is it likes to be just a general equation, right? So it's like solve for in terms of this, this, and this. So be careful. Make sure you solve them for the right, using the right variables that they want. Okay. So this is problem is going to be very heavily involved. And so what I'm going to do is I'm going to split this right into two parts. So this is going to be like A, B, and C, where we're going to use Gauss's law, and then we'll come back and do um, the three bullet points here on the right hand side, which is going to actually take up most of our space. Okay. So for part A, it talks about find Gauss's or use Gauss's law to find it between 0 and R, which is really inside the insulator. Okay. Now, what you're going to see is lowercase r, right? And so here's what we're going to do. So we're going to put a Gaussian surface in there, right, of radius little r. Okay. And we're going to go all the way out to r. And so we're going to use our equation, the surface integral of E dot dA equals Q enclosed, right, over epsilon naught, right? And again, don't be afraid of this surface integral. It's just going to be E times A, right? So E times A equals Q enclosed over epsilon naught. And so we know the area enclosed will be the area of a sphere. Okay. Now, what is that Q enclosed? So you have to understand that the Q enclosed comes from finding the total Q. And the way that works out, I'll do it here in a different color. So you're going to get Q total, right? Or sorry, Q enclosed is really just a portion of the total Q. And so that's going to be the volume of the Gaussian sphere, right, times the volume of the sphere itself. Okay, the Gaussian surface. We know they're both going to be 4/3 pi r squared, pi r cubed, but the big sphere is going to be capital R because it's going to be the radius all the way out, and the little sphere is going to be really the the of our Gaussian surface of lowercase r. So these 4/3 and the pi go away, and you find that the enclosed charge inside the insulator is simply going to be Q, which is our total charge, times the ratio of the radii. Okay, so I'm going to change this back to red. So what I'm going to do is I'm going to take that, and now that becomes my Q enclosed. So it becomes Q R. Oh, sorry, I hit the home button. So Q times little r over big R cubed, and we still have this epsilon naught. Okay, and so if we kind of and then we just divide that by 4 pi r squared, which gives us our K. So for the electric field inside the insulator, it's going to be KQ over R cubed times big R cubed times R cubed. Okay. And again, inside the insulating sphere, it's a portion of the total Q, right? And that's why we had to do that step here in blue. Okay. All right. For the next one, for part B, it's going from R to 2R. So basically, now we're going to surround our insulating sphere, which is now just going to be a point charge. Okay. And so, again, they want you to use Gauss's law, but this one really becomes pretty easy because now the charge enclosed is no longer a portion of it, it's the whole portion. So it's going to be E times A equals Q over epsilon naught. But again, it's a sphere, so it's going to be E times 4 pi r squared, right? And then if I solve this for E, guess what I get? End up getting KQ over R squared, right? And this would be, we'll call it little r, right? Because that's what they're using. So again, the reason why it's little, this KQ over R squared, is because it's a conducting sphere, right? That's how, it's a charged sphere. That's how it's a point charge. So that's how you think about it. Okay. Part C is probably the easiest question of all, right? This goes where we talk about conductors, right? Where we focus around conductors. So if you notice, it says between 2R and 3R. Well, guess what? That's inside this conductor, right? And what is the E field in a conductor? It is zero. So you really don't have to show Gauss's law here because, well, if you want to show it, you just say E dot dA equals Q enclosed, right, over epsilon naught. Well, guess what? The Q enclosed, if it's inside, is zero, right? So there's no charge inside because remember, all the charge sits on the surface, right? And so if this is zero, that makes my electric field zero. Okay, again, conducting material, right? That's why the E field is zero inside. Okay, now let's handle the more difficult ones, right? So now we're going to look at the potential difference. All right. So what happens is, imagine so for the first one, it says beyond 3R. So imagine we're at a point way out here, right? We're a distance x away, right? And so you have to notice that you've got to go through surfaces to get to this point. Okay. And so that's why we're going to go from infinity, right, to x, and then we may have to deal with this a little bit. We may have to deal with that a little bit. We have to deal with that a little bit. Okay. And so for the first bullet point, right, we're going to say, and we're going to use our integral. So we're going to say delta v equals negative integral E dot dr, right? And we're going to go from infinity to x, okay? And so what we're doing now is we're looking at, like, so again, this, you could treat this as a point charge, right? And so our total, and so this has a charge of little q, that has a charge of big Q, okay? And so our total charge for this would be big Q plus little q, right? And so when I go through and I do my potential difference, I'm going to say from negative infinity to x, right? My E field, because we just treat it as a sphere, will be E dot dr. So it's going to be kq over r squared dr, right? But my Q is going to be Q plus little q, right? Times K over r squared dr. And the negative k q plus q, right, is constant. So I'm just really integrating 1 over r, um, and this is from infinity to x, right? So it's going to be 1 over r squared dr. And so when I going through to get this, I'm going to say negative q plus q, right? The integral of 1 over r squared is negative 1 over r. Let me evaluate that from uh, infinity to x. So you can see, like, even though all this is going to equal our potential difference, right? And so we're going to, even though this looks like it could be difficult, it actually works out pretty easy, right? Negative infinity minus negative 1 over x. Okay, well, this is just going to be 0, right? Because it's 1 over a really large number, which is just 0. Uh, okay, and so our potential difference will be k q plus little q over x. All right. Um, and so what happens is, the reason why we get rid of the negative sign is because we will factor it in there somewhere. Okay. All right. For the second one, where we're going to go from within the shell, right? And so again, we're going to do negative, or sorry, delta v equals the integral of E dot dr. Okay. And so we have to split this up into two. So we have to go from, right? We have to go from infinity to the surface and then inside the surface. Okay, so we're going to go from infinity to 3r, right? So our limits of integration will be infinity to 3r, right? And then inside will be 3r to 2r, okay? And so if we split it up into two integrals, so we can say the from infinity to 3r e dot dr plus infinity from 3r really to x, sorry, because we're not going all the way to 2r, so to x, all right? Well, this is inside the sphere, right? And so that's just simply 0, okay? And we actually just did this, right? That's at the surface. It was our q plus q, right? So it would be delta v equals k q plus little q over, now it's 3r because now we have a defined point, right? So it's going to be 3r. So this will actually be our potential difference from going from infinity into the conducting sphere, right? Or into the conducting, yeah, that would be a sphere, right? Um, so just understand, again, inside a conducting material, right, the E field is 0, right? So that makes it a lot easier, even though it's like, oh my God, this looks like so hard. But it's easy because we talk about conducting materials, okay? All right, and so now we're going to do the whole thing, right? So now we're going to go, sorry, this should be an X. So now we're going to go in between really into the air, right? Between the outer shell to the inner sphere, okay? And so when we split this up, we're going to do the integral, right, from of E dot dr from infinity to 2r, right? And then we're going to go from 2r to x, okay? And so now we've done this, right? That's our KQ, right? Over 3R. Oh, sorry, I forgot to write the rest of this. So E dot dr, but we've done the first half of this integral, right? That's our answer to the previous one, is K Q plus little q over 3r, right? And even though we're going to 2r, remember the E field inside is 0. And so now we need to go from 2r to x, okay? And so the charge enclosed will be the isolating sphere, or the insulator, okay? And that's going to go again from x to r. And so we'll just say this will be kq, the integral of 1 over r squared dr, right? And it's going to go from 2r to x, and it's going to be kq 1 over r, right? Evaluated from 2r to x. And so what happens is we get that kq plus q over 3r with this term that will be kq 1 over x minus 1 over 2r. Okay, so this one's a little bit more, not necessarily more involved, because again, the integral is going to be the same. It's just going to, the answer is going to be 1 over r, right? Or negative 1 over r. Okay, and then you just simply, add that term to it. Here, let me write this a little bit nicer up here. So our answer for the last bullet point will be delta V equals K big Q time plus little q over r, or sorry, 3r plus KQ times 1 over x minus 1 over 2r. Okay, so that'll be our final answer for this part. Okay, sorry this video took a little long. Okay, and then the last time we're just going to wrap it up talking about these equipotential surfaces, and how do we handle those.